NICER's 2025 data just revealed neutron star radii cluster around 12 to 13 kilometers, forcing scientists to revise the dense matter equation of state that governs these cosmic objects. For decades, we've known these objects spin faster than helicopter blades, while packing the mass of our sun into a space the size of Manhattan. But these new radius measurements, combined with LIGO-Virgo's detection of neutron stars in the previously forbidden mass gap, have narrowed down the pressure inside neutron stars to values second only to black holes. This breakthrough constrains how matter behaves at twice nuclear density, conditions impossible to recreate in any laboratory on Earth. To understand how these extreme objects form, we must journey back to their violent origins, the stellar furnace that started it all. A massive star 8 times heavier than our sun begins this story, born from collapsing clouds of hydrogen and helium in a stellar nursery millions of years ago. This stellar giant ignites its nuclear furnace and sustains itself through hydrogen fusion for roughly 10 million years, with temperatures approaching billions of degrees as hydrogen nuclei slam together to create helium and release tremendous energy. Inside the core, thermonuclear fusion creates an outward pressure that fights against gravity's relentless pull inward. The star exists in perfect balance, with fusion energy pushing outward exactly matching gravitational force pulling inward. This equilibrium sustains the star's life, allowing it to shine brilliantly across the cosmos. But this cosmic furnace operates on borrowed time because massive stars burn through their hydrogen fuel at an alarming rate, consuming their nuclear fuel in a fraction of the time it takes smaller stars. When the hydrogen in the core finally runs out, the delicate balance that kept the star stable begins to shift. Without hydrogen fusion to provide outward pressure, gravity gains the upper hand. The core starts to contract under its own weight, and as it shrinks, the temperature rises dramatically. The compression heats the core enough to ignite helium fusion, creating carbon and oxygen in a new source of energy that temporarily restores the balance between gravity and radiation pressure. The helium burning phase marks the beginning of the star's death spiral. While hydrogen burning sustained the star for millions of years, helium fusion lasts only about 1 million years. The star has entered a period of increasingly rapid fuel consumption where each successive burning phase becomes shorter and more violent than the last. The star's outer layers begin to expand dramatically as the core undergoes these rapid changes, transforming the stellar giant into a red supergiant with a diameter that could encompass the orbit of Jupiter. The star races through its remaining fuel sources in an accelerating cascade of nuclear burning. Carbon ignites and burns for nearly 600 years, creating neon, sodium, and magnesium in increasingly complex nuclear reactions. Neon burning follows, lasting only about 1 year as neon atoms break apart and recombine to form oxygen and magnesium. Oxygen fusion creates silicon and sulfur in reactions that sustain the star for just 6 months. The core has become a layered structure, like a cosmic onion, with each shell burning a different element. Silicon burns in the innermost region, surrounded by shells of oxygen, neon, carbon, helium, and hydrogen burning in sequence. Silicon burning represents the star's last stand against gravitational collapse, creating calcium, titanium, chromium, and finally iron through a complex series of reactions that astronomers call the silicon burning cascade. This final phase lasts only days. Iron nuclei begin to accumulate in the star's core, and this marks the beginning of the end. Iron sits at the peak of nuclear binding energy, meaning it cannot be fused to release energy like lighter elements. When iron atoms fuse together, they actually absorb energy instead of releasing it. The star has reached a nuclear dead end where fusion can no longer provide the outward pressure needed to support the core against gravity. As iron accumulates, the core becomes increasingly unstable. Iron nuclei fill the center of the star like nuclear ash from millions of years of fusion burning. The temperature continues to rise, but no amount of heat can make iron fusion energetically favorable. The core grows more massive with each passing hour as silicon burning continues to produce iron in the surrounding shell. The star's core approaches the critical mass limit discovered by physicist Subramanian Chandrasekhar. When the iron core reaches approximately 1.4 solar masses, electron degeneracy pressure can no longer support it against gravitational collapse. The core has become a ticking time bomb, supported only by the quantum mechanical properties of electrons that resist being squeezed into the same energy states. Even this quantum resistance has its limits. As the iron core grows beyond the Chandrasekhar limit, the electrons and protons get crushed together with such force that they combine to form neutrons and neutrinos. This process removes the electron degeneracy pressure that was holding up the core, and gravity finally wins its million-year battle against nuclear forces. The stage is now set for one of the most violent events in the universe. The iron core has reached its breaking point, teetering on the edge of catastrophic collapse. 8 million years of stellar evolution have led to this critical moment where the fundamental forces of nature will clash in a battle that unfolds faster than human perception can follow. When giants collapse in milliseconds, the collapse happens faster than a single heartbeat. When the iron core reaches the Chandrasekhar mass limit of 1.4 solar masses, electron degeneracy pressure fails completely, and gravity wins its million-year battle in spectacular fashion. The extreme pressure forces electrons and protons together so violently that they combine to form neutrons and neutrinos in a process called neutronization. The core that once measured thousands of kilometers across shrinks to just 20 kilometers in radius within 1/100th of a second. This neutronization process releases an enormous burst of neutrinos that carry away 99% of the collapse energy. The neutrino detection from Supernova 1987A confirms this theoretical prediction when astronomers observed billions of these ghostly particles streaming from the explosion. Most neutrinos escape the star completely, but their detection provided direct evidence of the core collapse mechanism that creates neutron stars. The core reaches nuclear density when neutrons pack together so tightly that they touch each other directly. At this point, the core contains more mass than our entire sun compressed into a sphere smaller than Manhattan. The matter becomes so dense that a cubic centimeter weighs as much as a mountain. This marks where the collapse suddenly stops because neutrons resist being compressed further due to their quantum mechanical properties. The halt in core collapse creates one of the most dramatic reversals in physics. The infalling matter racing toward the center at tremendous speeds suddenly encounters the incompressible neutron core. This collision generates a shockwave that propagates outward through the star, marking the beginning of the supernova explosion that will tear through the star's outer layers. The shockwave races outward through the star's layers, carrying more energy than our sun will produce in its entire lifetime. The explosion tears through the star's outer envelope, blasting the hydrogen-rich layers into space at speeds exceeding 10,000 kilometers per second. The expanding debris forms a shock front that plows through the surrounding interstellar medium, creating a bubble of hot gas and radiation. The energy released during the supernova explosion staggers the imagination. In the span of a few seconds, the explosion generates more energy than 1 trillion suns combined. The explosion becomes so bright that it can be seen from distances measured in billions of light years, appearing as a new star in the sky that gradually fades over weeks or months. The supernova light curve follows a predictable pattern as different radioactive elements decay in the expanding debris. The initial flash comes from the shock heating of the outer layers. Over the following weeks, the light comes primarily from the decay of radioactive nickel-56 created during the explosion. This radioactive decay powers the supernova's glow for months after the initial blast. Most importantly, the explosion enriches the surrounding space with heavy elements forged through rapid neutron capture processes during the supernova itself. Gold, platinum, uranium, and other elements heavier than iron form in the extreme conditions of the explosion through what astronomers call the R process. These elements get dispersed into space where they can eventually become incorporated into new stars and planets, seeding the universe with the building blocks of complexity. While the outer layers get blasted into space, the core survives the explosion as a neutron star. The core's incredible density allows it to withstand the violence of the supernova blast. The newborn neutron star measures only 20 kilometers across, but contains 1.4 times the mass of our Sun. The surface gravity becomes 200 billion times stronger than Earth's gravity, creating conditions unlike anywhere else in the universe. The neutron star inherits the angular momentum of the original star's core. As the core collapsed, conservation of angular momentum caused it to spin faster, much like a figure skater spinning faster when pulling in their arms. The resulting neutron star can rotate hundreds of times per second, creating a cosmic lighthouse that beams radiation across space with each rotation. The magnetic field of the original star also gets compressed along with the core. The neutron star's magnetic field becomes trillions of times stronger than Earth's magnetic field. These intense magnetic fields channel particles and radiation along magnetic field lines, creating beams of energy that sweep across space as the neutron star rotates. The neutron star's surface temperature reaches millions of degrees immediately after formation. The heat comes from the gravitational energy released during the core collapse and from the ongoing decay of radioactive elements. The surface gradually cools over thousands of years, but the interior remains hot for much longer due to the star's incredible density and thermal capacity. From the violent destruction of a massive star emerges an object that challenges our understanding of physics. The neutron star represents matter in its most extreme form, where the normal rules of chemistry and atomic structure no longer apply. These stellar remnants spin and emit radiation for billions of years, serving as cosmic laboratories for studying physics under conditions impossible to recreate on Earth. For decades, astronomers thought they understood the basic properties of these exotic objects. The theoretical models seemed solid, the mass limits appeared well established, and the physics looked settled. But the universe had other plans, and 2025 brought observations that would force scientists to completely reconsider everything they thought they knew about neutron stars. The 2025 mass mystery that changed everything. LIGO-Virgo gravitational wave detectors began recording signals that defied theoretical predictions. For decades, physicists believed neutron stars had a strict mass limit around 2.2 times the mass of our Sun. This limit came from our understanding of how matter behaves under extreme density. Beyond this threshold, gravity should overwhelm any force that could support the neutron star, causing it to collapse into a black hole. The physics seemed clear and the mathematics appeared solid. Then the detectors started finding neutron stars that should not exist. The collaboration detected gravitational waves from neutron star mergers involving objects with masses reaching 2.5 solar masses. These observations shattered our confidence in theoretical predictions about neutron star maximum masses. The detected objects clearly exhibited neutron star characteristics in their gravitational wave signatures, yet they exceeded the mass limits that our best theories said were impossible. These discoveries forced physicists to confront an uncomfortable reality about the fundamental nature of matter itself. The signal designated GW230529 provided one of the most puzzling examples of this mass mystery. The gravitational wave detection revealed the merger of two compact objects with distinctly different masses. The lighter object measured between 1.2 to 2.0 solar masses, clearly within the neutron star range. The heavier object weighed slightly more than twice the mass of our Sun, placing it in a region that astronomers call the mass gap. This mass gap represents the mysterious zone between the heaviest confirmed neutron stars and the lightest known black holes. The mass gap has perplexed astronomers for years because stellar evolution models predict that objects in this range should be extremely rare. Stars that collapse to form compact objects in this mass range should either produce lighter neutron stars or heavier black holes. The existence of objects with masses in the gap suggests that our understanding of stellar collapse and compact object formation contains significant gaps. The 2025 gravitational wave detections revealed that these gap objects might be more common than previously thought. LIGO-Virgo detected 5 or 6 additional events involving neutron stars colliding with black holes throughout 2025. These detections provided crucial data about the mass distribution of compact objects in binary systems. The neutron stars in these systems consistently showed masses near or above the previously accepted maximum limits. The pattern emerging from these detections indicated that massive neutron stars might represent a significant fraction of the neutron star population rather than rare exceptions. The implications for nuclear physics run much deeper than simple mass measurements. The equation of state describes how matter behaves under extreme pressure and density conditions found inside neutron stars. This equation determines the relationship between pressure, density, and mass for neutron star matter. The 2025 mass measurements forced physicists to reconsider fundamental assumptions about how nuclear matter behaves at densities several times that of atomic nuclei. Previous equations of state predicted that neutron star matter would become soft at high densities, meaning it would compress easily under increasing pressure. Soft equations of state naturally limit neutron star masses because the matter cannot provide sufficient pressure support against gravity. The discovery of 2.5 solar mass neutron stars requires stiffer equations of state where matter resists compression more effectively at extreme densities. The stiffening of the equation of state at high density suggests that neutron star cores might contain exotic forms of matter not found anywhere else in the universe. Normal neutron star matter consists primarily of neutrons with small fractions of protons and electrons. At higher densities, exotic particles like hyperons, kaons, or even deconfined quarks might appear. These exotic matter states could provide additional pressure support that allows neutron stars to reach higher masses before collapsing. The boundary between neutron stars and black holes has become increasingly blurred by these discoveries. Traditional models predicted a sharp transition where neutron stars above a certain mass would immediately collapse to form black holes. The 2025 observations suggest a more complex picture where some objects exist in an intermediate state. These objects might represent neutron stars on the verge of collapse or exotic compact objects that are neither traditional neutron stars nor black holes. Some theoretical models propose that the most massive neutron stars might contain quark cores where the strong nuclear force breaks down completely. In these cores, quarks would exist as free particles rather than being confined within neutrons and protons. Quark matter could potentially support higher masses than conventional neutron matter, explaining how neutron stars reach 2.5 solar masses without collapsing. The transition to quark matter might occur gradually rather than through a sharp phase transition. Rotation might play a crucial role in supporting these massive neutron stars against gravitational collapse. Rapidly spinning neutron stars experience centrifugal forces that provide additional support against gravity. The most massive neutron stars detected through gravitational waves might represent rapidly rotating objects that can maintain higher masses than non-rotating neutron stars. The rotation would gradually slow down over time, potentially leading to delayed collapse. The 2025 discoveries suggest that neutron star physics operates in regimes where multiple exotic effects become important simultaneously. The combination of rotation, magnetic fields, temperature, and exotic matter states creates a complex environment where traditional approximations break down. Understanding these massive neutron stars requires sophisticated models that account for all these effects working together. The mass mystery revealed by 2025 gravitational wave detections has opened new frontiers in both nuclear physics and astrophysics. These discoveries demonstrate that neutron stars continue to surprise us with their extreme properties. But mass represents only one aspect of these cosmic objects. The forces that shape neutron stars extend far beyond gravitational attraction, reaching into realms where the fundamental forces of nature operate at their absolute limits. Magnetic fields that bend reality. The magnetic fields surrounding these stellar remnants represent the most powerful electromagnetic forces in the known universe. Neutron stars possess magnetic fields that are 1 trillion times stronger than Earth's magnetic field. These cosmic magnets create forces so intense they can literally bend the shape of atoms and twist the very fabric of space around them. Where Earth's magnetic field measures about 50 microtesla, neutron star magnetic fields can exceed 100 million Tesla, making them the most powerful magnets in the known universe. The 2025 radio telescope observations revealed magnetic field structures that challenged everything astronomers thought they knew about these cosmic dynamos. The European Southern Observatory's upgraded radio array detected complex magnetic field geometries extending far beyond the neutron star surface. These observations showed magnetic field lines twisted into helical patterns that spiral outward for thousands of kilometers. The field structures appear to change dynamically over timescales of hours or days, suggesting active magnetic processes occurring in the neutron star's magnetosphere. Advanced radiopolarimetry measurements captured the three-dimensional architecture of these magnetic fields in unprecedented detail. The data revealed that neutron star magnetic fields are far more complex than the simple dipole fields that scientists had assumed for decades. Instead of resembling a bar magnet with two poles, these fields showed multipole components with magnetic hotspots and cold regions distributed across the neutron star's surface. Some neutron stars exhibited quadrupole or octupole field components that created intricate patterns of magnetic field lines extending into space. The most extreme examples of magnetic field strength come from magnetars, a special class of neutrons, stars with magnetic fields, so powerful they affect the quantum vacuum of space itself. These objects generate magnetic fields exceeding 10 to the power of 15 Gauss, which is strong enough to disrupt the electromagnetic interactions between photons and virtual particle pairs that constantly appear and disappear in empty space. The vacuum polarization effect caused by these fields creates a form of magnetic birefringence where space itself becomes optically active. In 2025, the InSight HXMT team achieved the first direct measurement of a neutron star's surface magnetic field by detecting cyclotron resonance scattering features in X-ray spectra. The team discovered a cyclotron absorption line with an energy of 146 keV in the X-ray binary Swift J0243.6 plus 6 124, corresponding to a surface magnetic field strength exceeding 1.6 billion Tesla. This measurement provided concrete evidence that neutron star magnetic fields are significantly stronger than previous indirect estimates had suggested. These incredible magnetic fields serve as cosmic particle accelerators that can propel charged particles to velocities approaching the speed of light. Electrons and protons get caught in the magnetic field lines and spiral along them while gaining tremendous energy. The acceleration process occurs through magnetic reconnection events where field lines break and reconnect, releasing stored magnetic energy as kinetic energy of charged particles. These accelerated particles create the intense radiation beams that make neutron stars visible across vast distances. The magnetic field lines extend thousands of kilometers beyond the neutron star surface, creating a complex magnetosphere filled with charged particles and electromagnetic radiation. The 2025 observations revealed that these magnetospheres are not static structures, but dynamic environments where plasma flows along magnetic field lines at relativistic speeds. The interaction between the neutron star's rotation and its magnetic field creates electric fields that can accelerate particles to energies exceeding those produced by the most powerful particle accelerators on Earth. The lighthouse effect that makes pulsars visible results from the interaction between the neutron star's magnetic field and its rapid rotation. As the neutron star spins, its magnetic field sweeps through space like a cosmic lighthouse beam. The fastest spinning neutron star known, PSR J1748-2446 AD, rotates 716 times per second, making it one of the most rapidly spinning objects in the universe alongside other millisecond pulsars. Charged particles get accelerated along the magnetic field lines and emit synchrotron radiation that forms narrow beams extending from the magnetic poles. When these beams sweep across Earth's line of sight, we detect regular pulses of radio waves, X-rays, or gamma rays with precise timing. The timing precision of these pulses rivals atomic clocks, enabling astronomers to use networks of pulsars as gravitational wave detectors.